Homogeneous transformation matrix is a 4x4 matrix consisting of 3x3 rotation matrix combined with a 3x1 position vector along with an augmentation column that describes that transformation manipulator in a coordinate system. First, we get the rotation matrix of our manipulator. For the rotation matrix of our frame 0 and frame 1, we derive the stationary matrix and use the rotation matrix of z-axis for its moving matrix. So, z rotation So now, we have our z rotation. So, for deriving the stationary matrix of frame 0 and frame 1, x sub 1 is only projected to x sub 0. Y sub 1 is only projected to y sub 0. And lastly, z sub 1 is only projected to z sub 0. So we have r1, r sub 0 1 is equal to x. X1, y sub 1, z sub 1. So, multiplying the stationary matrix and the moving matrix, we obtain the rotation of frame 0 and frame 1. So, 0, 1, r is equal to 0. So we obtain the rotation of frame 0 and frame 1. Next, for the rotation matrix of frame 1 and frame 2, we derive the stationary matrix and use the rotation matrix of z-axis to its moving matrix. So we have z rotation Next is for deriving the stationary matrix of frame 1 and frame 2, x sub 2 is only projected to x sub 1. Y sub 2 is only projected to y sub 1, and the opposite direction, z sub 2 is only projected to z sub 1, but also in a opposite direction. So r 1, 2 is equal to x1, y1, so multiplying the stationary matrix and the moving matrix, we obtain the rotation matrix for frame 1 to frame 2. R12 is equal to 2, y sub 2, and z sub 2. So, half sign, negative, 0, negative, 0, 0, and negative. So now we have obtained the rotation matrix for frame 1 and frame 2. So for the rotation matrix of our frame 2 to 3, we derive its stationary matrix and use the identity matrix for its moving matrix. So we will have 1, 0, 0, 0, 1, 0, 0, 1, or 0, 0, 1. So, for deriving the stationary matrix for frame 2 to frame 3, x sub 3 is only projected to x sub 2, y sub 3 is only projected to y sub 2, and z sub 3 is only projected to z sub 2. So, r 2, 3 is equal to x 2, y sub 2, x sub 3, y sub 3, z sub 0, 0, 1, 0, and 0, 0, 1. So, multiplying the stationary matrix of frame 2 to, or multiplying the stationary matrix and the moving matrix, we obtain the rotation matrix for our frame 2 to frame 3. R 2, 3 is equal to can we change this? So now we have obtained the rotation matrix for our frame 2 to frame 3. So the derived position vector of our manipulator from frame 0 to frame 3 is this. P sub 01 is equal to A sub 2 cosine 1 A sub 2 sine theta 1 and A sub 1. So x sub 01, I sub 01, and z sub 01. So P 1 sub 2 is equal to A sub 4 cosine 2 A sub 4 sin theta 2 A3. Y sub 1, 2, and Z sub 1, 2. So P 2, 3, P sub 2, 3 is equal to 0, 0, A5 plus D3. So X sub 2, 3, y sub 2, 3, and z sub 2, 3. So this is the derived position vector of our manipulator from frame 0 to frame 3. So as I have said earlier, homogeneous transformation matrix is a matrix or is a 4x4 matrix consisting of a 3x3 rotation matrix combined with a 3x1 position vector along with an augmentation column that describes the transformation of a manipulator in a coordinate system. So for the homogeneous transformation matrix of frame 0 to frame 1, we will combine the rotation matrix and the position vector. So I already prepared this earlier, and then we will add the augmentation column. So we will have a result of this one. So we will just add the augmentation column. So cosine 1, sine 1, 0, negative sine 1, cosine 1, 0, 0, 0, 1, and then a sub 2, cosine 1, a sub 2, sine 1, a1, and then we will add the augmentation column, which is 0, 0, 0, 1. So we have here. So we have combined the rotation matrix and position vector for frame 0 to frame 1. For the homogeneous transformation matrix for the next frame, which is frame 1 and frame 2, we will be repeating the same process on getting the first homogeneous transformation. So use rotation matrix as the first 3x3. So H 1, 2 is equal to cosine theta 2, negative sine 2, 0, sine 0, 2, negative cosine 2, 0, 0, 0, negative 1, and then use the position vector for the next column. So A4, cosine 2, A4, sine 2, and then A3. Then we will just add the augmentation matrix on the last row, or below 0, 0, 0, 1. So now we obtain the homogeneous transformation matrix for our frame 1 and frame 2. After getting the homogeneous transformation matrix for frame 0 to frame 1 and frame 1 to frame 0 or frame 1 to frame 2, we will be using these two to get the homogeneous transformation matrix for frame 0 to frame 2. So to get the homogeneous transformation matrix for frame 0 to frame 2, we will be multiplying the two matrices that are mentioned. So H02 is equal to H01. We have H12. So we have cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2, and then sine theta 1, cosine theta 2, minus cosine theta 1, and sine theta 2, then 0 and 0. So next, cosine theta 1, sine theta 2, plus sine theta 1, and cosine theta 2. Then next is sine theta 1, sine theta 1, sine theta 2, plus cosine theta 1, cosine theta 2, then 0, 0. Next is 0, 0, negative 1, 0. Next is we have a sub 4, cosine theta 1, cosine theta 2, minus a4, sine theta 1, sine theta 2, plus a2, cosine theta 1. Next is a4 times sine theta 1, cosine theta 2, plus a4, cosine theta 1, sine theta 2, plus a2, sine theta 1, then a3, plus a1, then 1. So, this is the 4x4 homogeneous transformation matrix for frame 0 to frame 2. Lastly, in order to get the homogeneous transformation matrix for frame 0 to frame 3, we will be using the homogeneous transformation matrix, which is the frame 0 to frame 2 that was obtained earlier, and multiplied it with the homogeneous transformation matrix for frame 2 to frame 3, and just do the same process on getting the homogeneous transformation matrix for frame 0 to frame 1 and frame 1 to frame 0. So, we will get the value of is equal to 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and then 0, 0, A5 plus D3, and then 1. So now this is the 4x4 homogeneous transformation matrix for frame 0 to frame 3. That's all for homogeneous transformation matrix of a Scara manipulator. Thank you for watching.